Good evening. Today is this. We're doing the second part of our chapter on wave optics, and the topic that we'll be discussing today is interference. So, in the 17th century, there was this controversy on the nature of light. Newton supported the particle nature of light, and Huygens put forward the wave nature of light. But it was in 1801 that this scientist, Thomas Young, proved beyond doubt that light was a wave phenomenon. So he did that with his experiment on interference, and it is this experiment that we are going to discuss today. But before we go into this experiment of interference, let us discuss what are coherent waves. Now, if two waves, right now we are discussing light waves, and if two waves have the same frequency, the same wavelength, and a constant phase difference, then those waves are said to be coherent with each other. Now, when I talk about a constant phase difference, you know that I've already discussed with you that if you have a wave like this, points A and point B are said to be in phase because these 2 points happen to be at the same position, and also the wave is then going to attain the positive peak. But A and C are not in phase because even though they are at the same position, here the wave is attaining the positive peak, but here the wave is attaining the negative peak. Now, when we talk about two waves, we have already done this in our chapter on alternating currents. Suppose we have two waves like this. One wave is here, okay? And let's say we have the other wave like this. When this is at 0, this is at the negative peak. When this attains positive peaks, this attains 0 value, and so on, so that you will see that this wave is now like this, so that this point A and this point B are at the same position. You see, they both are at the equilibrium position, but here it is attaining peak value. So between this wave and this wave, we have a phase difference of pi by 2 because there's a pi by 2 angle difference between this wave and this wave, and that is the constant phase difference between wave 1 and 2. Suppose your next wave is, let's say another wave we have is like this. We have another wave. This is wave first one. The other wave goes like this. Okay. Now you will see that this point here and this point here are the same phase because both of them are in equilibrium position, but they are attaining the peak values. So now we have a phase difference of pi by 2 because this is 0, pi by 2, this is pi, and so on. So we have a phase difference of pi here. So these two waves maintain a constant phase difference of pi. So this is what I meant when I said two waves are said to be coherent. First condition is they must have the same frequency and therefore wavelength, and they must also maintain a constant phase difference. If they do that, then the two waves are said to be coherent. Now, if you take two independent sources like two different bulbs, then let's say this is one bulb and this is another bulb. S1 and S2 are the two sources, independent sources. Then they can produce waves of the same frequency and wavelength. But the problem is these waves that are coming out of S1 and S2 can never be coherent because the waves undergo abrupt phase changes. And the same phase change may not happen in this, and then if they do not maintain a constant phase difference, then they are not coherent, and because of this, two independent sources can never become coherent. So what Thomas Young did when he did his experiment is he took a screen, an opaque screen, and he pierced two pinholes in it, and then lit the two. So he took an opaque screen, made two pinholes, and he lit these two with the same source. So from the same bulb, we have light coming here and here. So this becomes the first source and this becomes the second source. So that now the waves that come out of these two will surely be coherent because they are produced by the same source, and any phase change happening here will be happening in both these, because both these sources or both these pinholes are lit by the same source. So the light coming out of this and this must have the same frequency, same wavelength, and also must have the same phase difference, must maintain a constant phase difference, because whatever changes happen here will be transmitted to the two sources also. So these are two coherent sources. Also, the two coherent sources need not have the same amplitude. They may or may not have the same amplitude. The amplitudes can slightly be different also. So now what happens here is, see, we know that this can be a source giving out spherical waves. So I'm going to draw spherical waves that come out of S1. So these are spherical waves. I'm just drawing it as but it's actually spherical waves. Okay. So we have spherical waves coming out of S1 like this, and also from S2 coming out of S2. Now if you keep a screen here, you will see these are waves coming out of S1 and S2. If you keep a screen here, you will see there are points like this where two waves are superimposing each other. You have learned in class 11 on the chapter waves what you mean by superposition principle. See, as a wave travels in a medium, it displaces the particles of the medium, and this displacement of the particle at any instant of time is what you call as y1 equal to, when you write the wave function, y equal to a sine omega t plus phi. You will see that this is the vertical displacement produced by any wave on a particle of the medium. This function you've learned in class 11 in the chapter waves. We also did this a sine omega t when we did AC currents. So a wave represented like this represents the instantaneous displacement. That is, at a particular time, what is the vertical displacement of the particle due to that wave traveling in that medium. Now suppose two waves are superimposing each other, and let y1 be the displacement produced by the first wave and y2 be the displacement produced by the second wave on the same particle at the same time. Then superposition principle says the net displacement is the algebraic sum of the individual displacements. So if y1 is the displacement produced on the particle of the medium due to the first wave, and at the same time another wave produces a displacement of y2, then the net displacement of the particle will be the algebraic sum of the individual displacements. So here what happens is, let us say at this point we have the two crests of a wave coming together. This is a crest here, okay, maximum amplitude in the positive direction. Suppose this particle is acted upon by two waves and both of them are displacing it to the maximum amplitude. Let's say this is, first one is displacing it by plus 2, this one. The second wave also acting on it is displacing it through plus 2. Then what happens? Y1 plus Y2 is plus 4. And you know that this being the maximum displacement is the amplitude. Intensity is the square of the amplitude, proportional to the square of the amplitude. So in our example, this will be amplitude is plus 4. The intensity is going to be 16. So all these points where two waves are acting upon the particle of the medium, superimposing each other, you will see that you're going to get a point of maximum brightness on the screen, which is what we refer to as a bright fringe or a bright band in interference. On the other hand, suppose we have two troughs, okay? Here all these points are acted upon by two troughs. Again, two trough would be here. So let's say one wave displaces it through minus 2, the other wave also displaces it through minus 2. Superposition principle says minus 2 plus minus 2, you should have a maximum displacement of minus 4. Square that, you still have the 16. So that means the intensity here produced on the screen when two waves superimpose each other will still be bright. So we have a band of maximum intensity which we call as a bright fringe or a bright band. Now here, suppose we have a crest and a trough superimposing. When the waves superimpose, let's say this particle is acted upon by a crest and a trough, then this would be a plus 2 and a minus 2, which means the amplitude is now going to be 0 and the intensity will also be 0. So that means on the screen here we have no intensity, zero intensity, which produces darkness, and such a point is what you call as a dark band or dark fringe. So you see that at all points here you could have either a bright band or a dark band because of the superposition of waves from two coherent sources. You will see on the screen you are going to get alternate dark and bright bands like this. Okay, so this is a screen that we are looking at. So instead of, usually if they are not coherent, if you switch on two bulbs, you will see that the whole screen is going to be brightly lit because of the light coming from the two sources. This whole screen will be bright. But if the two sources happen to be coherent, and if we have the phenomenon of interference, instead of seeing a totally bright screen, you will see that you have alternate dark and bright bands or alternate dark and bright fringes. This phenomenon is what you call as interference. So, in my room, if I have switched on two bulbs of let's say intensity I1 and I2, naturally my whole screen, that is my board, should be totally bright because I am lighting it with two sources of light. Now, if the two sources happen to be interference, to not two independent sources, two coherent sources, if I have two coherent sources and if the phenomenon of interference takes place, then it means that instead of seeing total brightness, I am going to see alternate dark and bright fringes on my screen like this, and this phenomenon is what you call as interference. So how do you define interference? Interference is it won't be so widely spaced, okay? Interference is a phenomenon in which alternate dark and bright fringes are formed on a screen due to the superposition of waves from two coherent sources. So I'll repeat once more. The phenomenon of interference is a phenomenon in which alternate dark and bright fringes are formed on a screen because of the superposition of waves from two coherent sources, and you know what coherent sources are. Now what we're going to do today is to derive an expression or a condition for constructive interference, which is when you have a bright band, and destructive interference, which is when you have a dark band. So let us say that we have two sources. Like before, we have two sources. This is S1 and this is S2. We have a screen here. At some distance, we have a screen. And there are two waves, one arriving from S1 and the other arriving at P from S2. Now naturally you will see from this figure that this wave from S2 has to travel a larger distance than the wave from S1 to reach P. That extra distance that the wave from S2 must travel to reach P is what you call as delta, which is called the path difference. So we are now going to see from our derivation what is the path difference that will give a bright band at P. What will be the path difference that will give you a dark band at P. Bright band at P is called constructive interference. Dark band at P is called destructive interference. Now S1, the wave from S1 I may write as A1 sine omega t, where we have already in the 11th standard used a sine function to represent our wave. So this is the instantaneous displacement. This is a maximum displacement called the amplitude. This is a frequency, and I will represent the next wave from the source S2 as A2 sine omega t plus phi, showing you that the two waves are coherent because they have the same frequency omega. They have a constant phase difference of phi, and if that happens, then the two waves are coherent. They can have different amplitudes which are slightly different from each other, or they can have the same amplitude. So superposition principle says the net displacement because of these two will be y1 plus y2, which means I may write this as a1 sine omega t plus a2 sine omega t plus phi. This sine a plus b, I can use the identity sine a cos b plus cos a sine b. Using that identity, I am going to expand this. So I may write y is equal to a1 sine omega t plus a2 bracket. Now I'm going to apply this sine a plus b. Okay. So this will be sine omega t cos phi plus cos omega t sine phi. I then open the bracket to get a1 sine omega t plus a2 sine omega t cos phi plus a2 cos omega t sine phi. Now you will see that this sine omega t is a function which keeps changing its value, because as time increases, omega t also changes and the value of the sine function keeps changing. But if you look at cos phi or sine phi, they are constant in time, because, for example, suppose phi is 60, t doesn't exist in this function. So let's say phi is 60, then cos phi can only have one value, half, throughout at all time. Sin phi, sin 60 can only be root 3 by 2. So cos omega t is a varying value function, but sin phi will have a constant value. So what I'm going to do next is, I'm going to take the variable outside, sin omega t bracket a1 plus a2 cos phi from here. a2 sin omega t is outside, cos phi plus, here I'll take cos omega t outside, and inside the bracket I keep the constant sin phi. Now I'm going to assume that this a1 plus a2 cos phi is a cos theta as my first equation, and that a2 sin phi is going to be a sin theta as my second equation. And then we are going to find out what values of a will stand this equation to be true. What values of a will give this equation, or the assumption that we have taken to be true for what values of a. Now why I did that is because now I may write this function as the net displacement y as, this is a cos theta, this whole thing. So I may take a outside, and in the bracket I have sin omega t cos theta. So this is sin omega t cos theta plus, here I am going to take this as a sin theta, right? So that a I have taken outside, so I will have cos omega t sin theta. So I may write cos omega t sin theta here, so that sin a cos b plus cos a sin b is going to be sin a plus b. So I may write this as a sin omega t plus theta as the net displacement or the resultant displacement, resultant wave represented by this equation. The amplitude of the resultant wave is a, which is what we are interested in, because the square of the amplitude will give you the intensity at P, and if it is maximum intensity, then P becomes bright. If it is minimum intensity, then P becomes dark. So basically, we are interested in the amplitude of the resultant wave. However, you will see that the resultant wave that is arriving at P will have the same frequency as the individual waves. Y1 and Y2 also have the frequency omega, and the phase difference of the resultant wave is theta with respect to the first one, Y1. So we have the resultant wave represented as y equal to a sin omega t. Now to find out this amplitude, because I told you we are interested in the amplitude, we will square and add equations 1 and 2. So when I square and add, cos square theta plus sin square theta will be 1. So I will have here a square on the right side. This is equal to, I'm going to square this and add the two together. So this will be a1 square plus a2 square cos square phi plus 2a1 a2 cos phi plus a2 square sin square phi. I have squared both and added. So now I have the equation as the amplitude is equal to, the amplitude here is equal to, this cos square phi plus sin square phi will be 1. So this will be a1 square plus a2 square plus 2a1 a2 cos phi, and this will be the intensity. A capital A is the amplitude of the resultant wave. So a square will be the intensity of the resultant wave. So this I may write as intensity of the resultant wave is This A1 is the amplitude of the first wave. So this will be I1 plus amplitude square of the second one will be I2 plus 2. This is just A1, A2. So root I1, I2 cos phi. You will see that from this equation, the intensity of the resultant wave at P actually depends on cos phi. When cos phi takes maximum value 1, here intensity at P will be maximum and you get a bright band at P or constructive interference at P. If cos phi takes the minimum value, that is -1, then you have a dark fringe at P or destructive interference at P. So that's what we are going to do. The conditions when you can get a destructive interference and a constructive interference. So for a bright band, we know, or for constructive interference, we know cos phi must take maximum value, that is 1, so that I is maximum. So cos phi should be equal to 1, which means phi can have value 0 because cos 0 is 1. Then the next value is 2 pi, 4 pi and so on. Or delta equal to, see, if you have a wave like this, we know from this point here to this point here, the total distance is what you call as lambda. And that distance is what we call as the path difference. So whenever the path difference is lambda, we see that the phase difference, that is the angle covered, will be 2 pi, right? Because this is 0, this is pi by 2, this is pi, this is 3 pi by 2 and this is 2 pi. So always keep in mind that a path difference of lambda corresponds to an angle difference or phase difference of 2 pi. So if phi is 0, then the path difference is also 0. If it is 2 pi, then we know it is lambda. If it's 4 pi, then we know it is 2 lambda and so on. Or if I write a general condition, delta is equal to n lambda, where, I hope you can see that, the general condition will be n lambda. So I'll write it here. Delta should be n lambda for it to be a bright band. So that when n is 0, we have delta as 0. If it's 1, lambda. If I put n as 2, then we have 2 lambda and so on. So that means n can take values 0, 1, 2, 3 and so on. Now if you want a dark band, if it's a dark band or destructive interference at P, then we know that cos phi will be taking the minimum value, that's -1, or phi -1 is when it is cos 180 is -1, pi, 3 pi, 5 pi and so on, or delta will be, see, here we are talking about pi. Pi means half of this. So that means this distance will be lambda by 2 whenever the phase difference is pi, right? Because it's half of that wavelength. So pi corresponds to lambda by 2, 3 lambda by 2, 5 lambda by 2 and so on. And you will see these are all odd multiples of lambda by 2. So if I write the general condition, then I may write this as, I'll write it here because I think you can't see. So this condition is delta must be an odd multiple, that is 2n plus 1 lambda by 2, because 2n is an even number, plus 1 you will get an odd number, lambda by 2. If the path difference is 2n plus 1 lambda by 2, you get destructive interference or dark band at P. That means, see, suppose let's say we have the center of the screen, okay? At the center of the screen, if I put n equal to 0, you see delta. Here, if I put n equal to 0, then I get the path difference as 0. So when path difference, there is no path difference if they are arriving, if there is no path difference between the two, when they are arriving at the center, then that means delta is 0, no path difference. That means at the center you are going to get a bright band. Okay, because you can never get this as 0, right? Because even if you put n equal to 0, delta will still be lambda by 2. So you can't have a dark band at the center. That means when the path difference is 0, you can only have a bright band. Now suppose at this point, another point here, I'm taking another point here. The path difference is, let me rub this off. the path difference is 1 complete lambda. So path difference is 1 complete lambda. That means if I put n equal to 1, then delta is 1 lambda. If it is 1 lambda, then you get again at P a bright band here. Or if this could be, let's say, 2 lambda, even then point P is going to be a bright band, because every integral multiple of lambda for path difference will correspond to constructive interference. On the other hand, if this path difference is an odd multiple of lambda, that means, let's say we have a point on the screen, P, where the two waves are arriving such that the path difference is, let's say first one, let's say 1/2. That is, you have, this is how much? 1 crest only. So path difference is lambda by 2. That means if I put 0 here, then delta is lambda by 2. So when path difference is lambda by 2, it corresponds to destructive interference. The next value will be, if I put 1 here, then that will be 3 lambda by 2. That is 1.5 lambda by 2. Which means you have a complete lambda and a half. 1.5. So that is 3 lambda by 2. Even then you will have P as dark. So we have now derived conditions for constructive and destructive interference, and we have arrived at the condition that whenever the path difference between the two waves is an integral multiple of lambda, then point P on the screen is going to be a bright band. But if the path difference is an odd multiple of lambda by 2, then point P is going to be a point of destructive interference or a dark band. Thank you.